When building user interfaces for developer platforms or frankly for anything else, we tend to focus mostly on web UIs. That's why there is a surge in popularity of portals like Backstage, Port, and many others. Still, user interfaces can have many other forms, and more often than not, a single one is not enough. The truth is that some forms are more appropriate for some tasks, while others for other tasks. For example, observability in any form tends to work the best with web UIs or desktop applications. We need that rich experience to visualize charts and graphs. While that can be done from, let's say, a terminal, we often need more. On the other hand, while some might prefer to do operations also from a web UI, others, me included, might prefer CLIs. Similarly, if you want to automate something, there isn't much choice beyond writing scripts and executing them from workflows like GitHub Actions, Jenkins, Argo workflows, or whatever else we might be using. Then there are IDEs like VS Code and JetBrains, which are yet another type of user interface that tends to be better suited for certain type of tasks like coding than using web UIs or terminals. Right? What I'm trying to say is that there are many types of user interfaces and we should not be focusing only on web UIs. In that spirit, today we will explore CLIs. To be more specific, we'll explore how we can create our own CLIs that will do exactly what we need them to do. Today, we will build a proper platform CLI. We can see a glimpse of what it can do through help. It will be a CLI that will enable us to perform any of those tasks specified through that auto-generated help. More importantly, we'll make it in a very easy way. It will be a proper CLI that anyone can create easily. Let's start with why. Why we might want to build our own CLIs. After all, we can use existing CLIs like, for example, CURL that can send HTTP requests to any API. The problem with CURL or curl and other similar CLIs is that they are low level. We could, for example, use it to communicate with Kubernetes API, but that would be painful, really painful and complicated and not very user-friendly. That's why we have higher level CLIs like, for example, kubectl. By the way, I'm using APIs as examples. CLIs come in many flavors. They're certainly not limited only to APIs. So I'm using them only as examples in this video, just to be completely transparent and clear. As an example, we could use kubectl to retrieve all resources based on definitions that are baked into Kubernetes. Kubectl is very generic, and we can use it to work even with custom resources, even though it has no idea, and literally no idea, what they are. Anyways, kubectl is great, in part because it's dynamic. Yet, it can also be complicated for the same reason. For example, if you would like to retrieve all the crossplane resources related to the claim that I applied earlier, we would need to execute kubectl get, followed with a list of resource types that might be a part of it, and then making the selection with -- selector that filters it by the claim name label set to silly demo. That was painful, right? And it was painful in big part because kubectl is dynamic but also generic. It's supposed to work with anything available in Kubernetes, and as is often the case, that makes it not excel at anything specific. As a result, we might want to use a more specific CLI, like in this case would be Crossplane, which, among other things, allows us to trace all the resources related to a claim. All the examples we saw suffer from the same issue. They're generic. CURL was designed to work with any API, but arguably it is the worst for any specific API. kubectl is more specific since it works only with the Kubernetes API, yet it is also the most generic one we can use if the scope is limited to Kubernetes. Finally, we saw the Crossplane CLI, which is more specific. It is arguably the best one to work with Crossplane resources in Kubernetes clusters, yet at the same time the most limited since it cannot do anything else but work with Crossplane resources. So, why am I explaining all that? Well, I'm trying to make a point that we need both generic but also specialized CLIs that are focused on a specific task or a specific platform. Even though we could operate AWS, Azure, or Google Cloud with CURL, we are much better off with using AWS, AZ, or G-Cloud CLIs. Even though we could use CURL with Kubernetes, we are better off with kubectl. Within the Kubernetes ecosystem, if, for example, we would like to work with Istio, we can do it with kubectl, but we might be better off with Istio control. More specific CLIs tend to be better at more specific tasks, but they do not exclude the usage of more generic CLIs. We need both. Here comes the question though. If you're building an internal developer platform or an IDP, is it enough to operate it using only more generic CLIs like kubectl, CURL, and others, or should we have a CLI that is specifically designed for that platform? And here it comes. I think that the answer is yes to both. Some of us, if not all of us, should continue using more generic CLIs, but we should provide a platform-specific CLI as well. But here comes the problem though. If you want to have a platform-specific CLI and that platform was built by us, that CLI needs to be built by us as well. It does not have to be the only way to interact with the platform, but it should certainly be one of the available interfaces. And here comes another potentially more important question. How do we build such a CLI? When building CLIs or any other type of executables that should essentially run tasks, people tend to choose either Bash or a programming language like Go or Python. Both of those choices come with their own set of problems. Scripting languages like Bash are great for internal use CLIs, mainly because they are a very easy way to wrap other CLIs. More often than not, when we are building a CLI that will be used internally, much of the functionality can be accomplished by wrapping other CLIs. It might need to be sending requests with CURL, or it might be doing some funky stuff with kubectl, or it might be modifying YAML with YQ, and so on and so forth. There is an infinite number of things that we might need that could be accomplished by wrapping other CLIs. There are a couple of problems with Bash and other scripting languages though. To begin with, they are not real, whatever real means, programming languages. Adding logic can be cumbersome. There is no compilation, so it's hard to find out the issues until we hit them at runtime. Everything is treated as text, so it's hard to pass data from one instruction and process it in another. Maintaining anything but simple scripts can be a burden. The alternative is to use a real language like Go or Python or whatever one might be comfortable with. That is certainly a great choice when working on an external CLI, since we can, in some, but not necessarily all cases, compile them into a single executable self-sufficient binary, making it easy to distribute and install. We get code completion and other nice things available in IDEs. However, as I already mentioned, internal CLIs tend to rely heavily on other CLIs, which essentially means that a significant part of our CLI is about execution of other binaries. That tends to be cumbersome in real languages. They were not designed to do what scripting languages do. Also, they are much harder to iterate fast. Typically, a single line of a Bash script often results in multiple lines of code in other languages. So, neither scripting languages nor real programming languages are a good choice. Each has its own pros and cons, and I ended up going from one to another frequently. I would often start with a Bash script, get annoyed when it gets a bit larger or more complex, then switch to Go, only to get annoyed again with its verbosity and annoyances that make it relatively complicated to do things that are simpler in Bash. As a result, I have been switching back and forth until I discovered Nushell. Nushell gives me the best of both worlds. It is a scripting language, so it's just as easy to execute other binaries as when you're working with, let's say, Bash. On the other hand, it is a compiled language, so I get to detect many of the issues before scripts are executed. Finally, output of its instructions is structured data. So processing outputs is very easy and very intuitive. As a result of all that, and quite a few other reasons, Nushell became my go-to language when building internal CLIs. I still don't think it is a good choice when working with those that are distributed to external users. I would not rewrite kubectl, Crossplane, or any other similar CLI to Nushell, but for internal usage, it is, at least in my opinion, the best choice, especially for those organizations who adopted Nix packages. Let me show you an example I wrote for a group of videos I'm working on right now. Please note that this video focuses on reasons why Nushell might be a good choice for building internal CLIs. If you're new to Nushell, you might want to watch that video first. And the link is in the description, by the way, so go down there, check it out. There are a few things I feel are important when building internal CLIs. It needs to be a proper CLI that allows us to execute different commands with mandatory or optional parameters. I need it to be able to show help that explains how to use any of the commands it provides. It needs to have the option to load shared code in some form or another in case there are reusable pieces across multiple CLIs or as a way to organize code. It needs to be able to execute other binaries, other CLIs easily, without much, if any, boilerplate code. It needs to be able to produce outputs from either binaries or libraries as data so that it can be processed easily. Finally, it should be a single executable so that the distribution is easy. Let's see whether Nushell can give us all those features, and if it can, how do we get them? We'll use a CLI I built for a series of videos to demonstrate the good and the bad. Here's the output of my platform CLI with the --help argument. That looks like a proper CLI. Whomever is unsure what is available can simply execute help and get a list of the commands with the description what each of them does. I even removed the .new extension since it is irrelevant for the users, for developers, in which language it is written. If you would like to get more information about one of those commands, we can execute platform, type the command we're interested in, like build image, and finish with --help. That is everything, and everything one might need to know how to build and push images. In this specific case, the tag is mandatory, and there are optional registry image and push flags, each with the description and, if available, default values. And here's how I added help to all the commands in that CLI. To begin with, all the definitions that start with main are automatically converted into commands, and more importantly, at least for the current discussion, automatically output when we add the --help argument. The comment on top of each, as for example the one above run unit tests, automatically becomes the description of that same command. Finally, each parameter and flag can have a description which is a comment on the right side of it. And that's it. It's as easy as it can get. And all we have to do is adopt a few simple conventions. Now that we mentioned parameters and flags, let's see them in action and see how they're defined. As we saw with the help output, commands can optionally have arguments, or as Nushell calls them, parameters and flags. For example, if you would like to build latest image that is also tagged as 1.2.3, but we would not like to push that image or those images to the registry, we can execute platform build image with the tag 1.2.3 and set the --push flag to false. That command is a replacement for a few Docker commands. It built the image with the specified tag, then it created the latest tag of that same image, and it skipped pushing both to the registry because we told it to do that, to skip it. As we saw through the help, we could have specified the registry and the image name, but we didn't, so the command used the default values for those. And here's how that was done. Each main command can be without any parameters and flags by specifying an empty array, as is the case of run unit tests. The build image command, on the other hand, has both a parameter and a few flags. Parameters like tag are not named, When we executed platform build image, we added 1.2.3 without specifying what it is. Parameters must be set in a specific order simply because we set only their values. Arguments, on the other hand, are named. If, like we saw when we executed the command, we want to tell it not to push images, we have to set --push before the value. In this case, true or false. Both parameters and flags can have default values, like for example in the case of registry, which, if not specified, will be set to ghcr.io/freeparsec. Default values are specified with the equal sign followed by some value. In those cases, we don't have to specify the type. Nushell will automatically deduce, depending on the value itself, whether it is a string, boolean, integer, or whichever other type is available. Bear in mind that in the case of flags, we are using variables without --, as for example is the case with the registry. --, is there only to tell Nushell that we want to have a named flag. Now, let's move to the next requirement and see how we can organize the code and have reusable pieces. Unless we are working with a relatively small amount of code, we often want to separate it into logical units. That's what I did with the files in the scripts directory. By having the code in separate files, we can accomplish two distinct objectives. First, it is often easier to keep the code in different files. It simply is. In this case, there is Argo with the code related to Argo CD, Crossplane for operations related to Crossplane, Kubernetes that creates and destroys different types of Kubernetes clusters, and so on and so forth. That way, the main file, in this case platform, is relatively short, or as is my case, only contains the parts that are unique to that CLI. And that brings me to the second, even though probably unique to me, possibility. I have a library of functionalities in a separate repository. That way, when I'm building a CLI that is used in a specific project, I can simply copy those that I need and leave out those that I don't, thus keeping it minimal and not encumbered with commands that the project does not need. Let's, for example, take a look at Kubernetes. There is no functional difference between the code in that file when compared with the platform we executed and saw earlier. It contains two definitions: main create Kubernetes and main destroy Kubernetes, each of them having some parameters. The only thing that makes them special is that I was too lazy to write comments, so you won't see a fancy output with help. Still, even in that case, help with a list of parameters is available automatically. Now, let's take another look at the platform. Code is imported by sourcing it, as for example in the case of Kubernetes new. From there on, the commands, those prefixed with main, are automatically included by executing that CLI. We can invoke it from some other definition, like for example, main create Kubernetes kind, executed through setup all. At the same time, those source definitions that are prefixed with main are automatically available as separate commands in the CLI. We can see that by, for example, executing platform create Kubernetes --help. There we go, it works. The code is included. Any definitions can be executed from inside the main one, the one that sourced it. On top of that, those prefixed with main are automatically available as separate commands, and that is awesome. Next, let's talk about execution of binaries. Some more generic languages are frankly painful to work with when trying to execute shell commands. With Go, for example, we have to use exec.command, pass it the command and all the arguments as an array, then capture stdout and stderror as variables of the output, do some error verification, and whatever else needs to be done. Shell scripts do not need any of that. We just specify what we want to execute and that's it, most of the time. Nushell is a shell programming language. As such, just as with Bash, there is nothing special we have to do to execute other shell commands. We can simply execute any command that is available in the path. And here's an example. Over there, we simply execute docker image build, followed with docker image tag, and finally docker image push, twice. It's the same as with Bash or any other shell scripting language. It just works. And we can move to the talk about data. Most of the time with internal CLIs, we execute some commands, parse the output, and use it as input of other commands. Nushell, just as Bash, does that by piping data from one to another command. What makes it special is that outputs are not text blobs, but structured data. As such, we know what the data is, and we can do some funky stuff to filter and manipulate it. Here's an example. Inside the update GitOps definition, we are using open to read contents of a YAML file. Since it knows that it is YAML, it knows how to transform the text in that file into its internal data format. That structured data is then passed to upsert instruction that changes the value of spec parameters image entry in that data to the combination of registry image and tag variables. From there on, that modified data is sent still as data, not as text, to the save command that transforms it to YAML and saves it back into that same file. That block of code is similar to what we would do with, let's say, YQ, except that we do not need any external binaries. Instead, all is done using Nushell's internal instructions. Every Nushell instruction or command outputs data, and each is capable of taking data as input. It's not text, it's data, and that makes it very, very special. Even if we try to execute shell commands that are not available in Nushell, we can use it to transform almost any text blob into data. Here's an example. The getIngress definition, among other things, executes kubecontrol to retrieve YAML representation of a service. The output of that command is not YAML or any other data structure. It looks like YAML, but is actually a text blob. If that text would be a file, Nushell would know from the file extension how to transform it from YAML to its internal data format. But in this case, it is a text output from an external command. So we are helping Nushell know what the text format is by specifying that it comes from YAML. From there on, it is pure data passed to the get instruction that retrieves status load balancer ingress, the first index in ingress, hostname value, and stores it into the ingress underscore hostname variable. And there is only one requirement left. Can Nushell scripts run as single self-sufficient executables that can be distributed as a binary? If, for example, we would be building a CLI with Go, we would probably produce executable binaries for each operating system. From there on, users would not need to have a Go compiler or any other prerequisites to run it. That's how, for example, kubecontrol works. We just download it and run it. There are no dependencies of any kind. Can we do that with Nushell? The short answer is no. A slightly longer answer is no, and even if we could, we shouldn't. One big advantage of scripting languages like Bash is that they are both executable but also in clear text. Anyone can modify it and run it right away without compilation. Nushell is similar, but unlike Bash that runs anywhere, we need to have Nushell installed. From that perspective, it is closer to, let's say, Python, except that we can run Python code as is, as long as we have Python installed, or we can package it into a self-executable binary that does not require separate installation of Python runtime. With Nushell, the latter is not, as far as I know, possible. Still, as I mentioned, I don't think that we should be compiling internal tooling and distributing executables, since that would complicate fast and easy modifications. If, for example, we have a CLI related to a project or let's say a platform, it is very convenient to be able to quickly modify it to either fix a bug or add a new feature or whichever other reason there might be. So it does not matter that it cannot be compiled to a binary, except that everyone using our CLI made with Nushell would need to have Nushell runtime installed. That's a potential problem for some. In my case, that is not really any issue, since I think that everyone should be using Nix packages, in my case through DevBox. In such a case, Nushell is yet another package that is installed when working on a project or with an internal platform. We need packages anyway, since those internal CLIs often depend on other third-party CLIs like kubecontrol and Helm and whichever else we might be using, and they're wrapping those into internal CLIs. So that's it. Try it out. I'm convinced that you'll find Nushell very useful if you're trying to write internal CLIs or any other type of scripts. Let me know in the comments what you think of Nushell and what is your favorite language to write internal CLIs. Thank you for watching. See you in the next one. Cheers.